Okay, now let's explain how AdaBoost works. So the first step is basically we have a weak classifier, and we said that the weak classifier can be a decision stump, for example. And this weak classifier is made on top of the training data based on the weighted samples, right? We have a weight for each sample. So each sample weight indicates how important it is to be correctly classified. So initially, for the first stump, we give all the samples equal weights, right? So first we have equal weights for all the training examples, okay? And then we create a decision stump for each variable and see how well each stump classifies samples to their target classes, right? So we have a number of decision stumps equal to the number of variables we have. So if we have 10 features or 10 variables, then we will have 10 decision stumps, right? So for example, let's look at this diagram. We want to check if a person is fit or not, so we will classify it as either fit or not. So what are the features? We have the age, eating junk food, and exercise. So we have how many decision stumps? We have 3 decision stumps, right? So we would look at how many samples are correctly classified as fit or not for each individual stump. So as you can see here, we have age, we have eats a lot of junk, and then we have exercises in the morning. Okay, so we will say this is the complete decision tree. If we build a complete decision tree, we will first classify based on the age. So if this person is younger than 30, right, is below 30, then we will check if he eats a lot of junk food or not. If yes, then this person is unfit. If no, then this person is fit. Okay, and if he is above 30, then we will check if he exercises in the morning. If yes, then this person is fit. If no, then this person is unfit. Okay, very, very simple if we use a decision tree. Now, if we use decision stumps, then we are going to build 3 decision stumps, and we will make the decision based on each individual decision stump, right? So we will look at the age. If it's less than 30, then yes. If no, then this person is unfit, right? So yes, no, yes, no. So we have 3 decision stumps, and we will classify based on each of them. Okay, so this is how we build the decision stumps. Okay, now more weight is assigned to the incorrectly classified samples so that they are classified correctly in the next decision stump. Okay, so this is the third step. And weight is also assigned to each classifier based on the accuracy of this classifier, which means high accuracy equal high weight, right? So this can be a little bit confusing because we are assigning 2 weights here. We are assigning a weight for each decision stump or each classifier, and when we put high weight for this classifier or give high weight to this classifier, then this means that this classifier is giving us higher accuracy than the other ones, right? But for the weight for the samples, if we have higher weights for some samples, then this means that these samples are incorrectly classified, right? So they are opposite from each other, right? So this is different from this one. Okay, now we reiterate from step 2, right? Step 2 is basically creating a decision stump for each variable, right? So we iterate again from step 2 until all the data points have been correctly classified or the maximum number of iterations have been reached, right? So we have a maximum number of iterations, let's say 100. So if we reach 100, this is the best accuracy we can get. Otherwise, if we don't really have a maximum number of iterations, then we will wait or continue iterating until all the data points are correctly classified, right? So we have here, first we classify based on the age, then we classify based on eats a lot of junk or not, and then exercises in the morning or not. And let's say, for example, we have a 4th variable for 8+ hours of sleep or not, right? So this is how we are going to build the decision tree, right? Or build the AdaBoost algorithm based on decision stumps. Okay, so this is basically how the algorithm of AdaBoost works. Okay, now let's look at the AdaBoost equation, right? So this equation can be a little bit daunting at the beginning, right? Because here we are saying alpha of t is half len. Len is basically the logarithm of 10, right? And len of what? 1 minus total error over total error. So what do we mean exactly by this? We don't really need to know the details of how we got this equation, right? We don't really want to know the derivation for this equation, okay? But what do we need to know is what this equation actually means, right? The intuition behind this equation. So alpha is basically how much influence this decision stump will have in the final classification, right? So this is basically the weight of each decision stump, right? So t is corresponding to the current decision stump, okay? And the total error here, you are seeing here, is nothing but the total number of misclassification for the training set divided by the training set size, right? So the percentage of incorrectly classified samples. Okay, so this is basically the total error. And let's look at the graph here, right? So if alpha is 0, so this basically means that the total error, right, or the error rate is 0.5. So if we put 0.5 here, we will have 1 minus 0.5, right? So we have 0.5 over 0.5. So this is 1. And then we have here half of len 1, so this is basically 0. Okay, so alpha is 0 when the error rate is 0.5. So when alpha is 0, the error rate is equal to the random chance. You need to understand that the maximum error is not 1, right? So the maximum error is not 1, because if we have a maximum error of 1, so we misclassify all the points, so this means that this classifier is actually working greatly, but we just need to flip the classification, right? So if it's a binary classification and each time this classifier is giving us incorrect classification every single time, then we just need to get this classification and flip it, right? So if this decision stump is telling you that this should be 0, then we will say it's 1. If it's saying it should be 1, then we will say it's 0, right? So if the error rate is 1, then this specific decision stump is actually giving us an accuracy of 100%, right? So the maximum error rate is actually 0.5, because this way it's basically random chance. 50% of the time it's classifying the data correctly, and the other 50% of the time it's classifying the data incorrectly, right? So if alpha is a positive number, like here, right? If alpha is 1, this means that the error rate decreases, right? When we go to this direction, so when alpha increases, the error rate is decreasing, right? So this means we have a perfect decision stump, right? So if alpha is a positive number, the error rate decreases, which means we have a perfect decision stump. And here we have W of I, right? So this is different from alpha. W is basically for each sample, right? We give a weight for each sample. So the weight for each sample equal to the weight of the previous iteration, right? Or the previous weight for this specific sample times e power alpha, and this alpha can be positive or negative. So let's understand what we mean exactly by this. When alpha is positive, right? When alpha is positive, then the predicted and the actual output agree, right? So basically the sample was classified correctly. In this case, we decrease the sample weight from what it was before, since we already performing well, right? So if we go back here, you will see that we are giving here smaller weight for this, right? Or after this iteration, we're giving a smaller weight for x1, because basically this decision stump decided that this is actually correct, right? So in the next iteration, we don't really want to focus on this sample, right? So that's why we will decrease the weight for this specific sample in the next iteration, or for the next decision stump. if alpha is a positive number, then we will decrease the weight, right? So here we have e power negative alpha, we'll have e power negative alpha. So basically this number will decrease. We will be multiplying alpha by a number less than 1. So that's how this weight will decrease. On the other hand, if alpha is negative, right, this direction here, then this means that the predicted output doesn't agree with the actual class, which basically means this sample is misclassified. And in this case, we need to increase the sample weight so that the same misclassification doesn't be repeated in the next stump, right? We don't really want to repeat this misclassification for the next stump, okay? And this is how the stumps are dependent on their predecessors, right? So this is basically how the AdaBoost works, right? So we have alpha for each decision stump. And after we find alpha using the total error, which is the misclassification divided by the training set size, we will just update the weights for each sample for this decision stump, right, given the last weight or the previous weight for this specific sample. We will increase the weight of this sample if this stump is actually misclassifying this point or this sample, and we will decrease the weight if this decision stump is classifying it correctly, right? So now let's look at the AdaBoost pseudocode, right? So this is basically how the algorithm works again. We initially set uniform example weights, and for each base learner, so base learner here we mean decision stump, for example, right? For each decision stump, what we are going to do is that train base learner with a weighted sample, okay? Test base learner on all the data, set learner weight with a weighted error, right, the alpha, okay? And after that, set examples weights based on the ensemble predictions. So we will get alpha for each decision stump and then get W's for each sample and repeat the process again and end for, right? So this is basically the AdaBoost pseudocode. Now, if we want to have a comparison between bagging and boosting, we can just say that bagging is easy to parallelize and hence the training is faster. So training bagging is much faster than boosting, but at the same time boosting is more efficient for fixed number of iterations or classifiers. If we have a fixed number of iterations or a fixed number of classifiers, then boosting will work much faster than the bagging algorithm, and it will give you better results. But generally speaking, you need to test both, right? You need to test bagging and you need to test boosting and see for this specific data and for this specific problem which one of them is giving you better results. And if you want to know more about bagging and boosting, and if you want to dive deeper, even deeper, I will give you some resources, right? Here, what is AdaBoost Optimizer, right? For in this blog, they are talking about AdaBoost Optimizer in very detailed explanation. So if you want to check this and send me a message or ask in the Q&A, that would be great, right? Now, in the next lesson, we are going to start introducing the project for this section, right? In this section, we are going to work on a project for predicting the selling price of the vehicle dataset. And this is a dataset available on Kaggle, right? What we are going to do is that we are going to load the dataset, perform all necessary data exploration and pre-processing, and then perform proper hyperparameter tuning to choose the best base model, depth, maximum features, and any other important hyperparameters. And of course, we are going to do all this from scratch, right? So we can use our own implementation for the ensemble learning, or we can use the sklearn implementation, but otherwise we will go to this project step by step until we finish it and find a very good result, right? So let's go to the next lesson and start working on the project. Let's go.